Welcome back. We're going to graph a few more functions here. So let's take a look at the function f of x equals x plus 2. Okay, so the first thing we want to do is we want to construct a table of values, including our domain and our range. Alright, so let's go ahead and once again, we need to be smart. We want to think about the values that we're choosing. And we want to look at our function and make sure that there's no values that we need to watch out for, like division by 0 or anything like that. X plus 2 is about a simple linear equation that you can actually find, so let's go ahead and use the points that we've been using. Minus 2, minus 1, 0, 1, and 2. Alright, so let's go ahead and find f of minus 2. When x is minus 2, the function minus 2 plus 2 equals 0. F of minus 1 plus 2 is 1. F of 0 is 0 plus 2, which is 2. F of 1 is 1 plus 2 equals 3. And you can kind of see where it's going. F of 2 is 2 plus 2, which is 4. So now we have a significant table of values that we can use to graph this function. So let's go ahead and do so. This is our f of x axis. F of x, this is our x axis. Alright, so now we have 5 points that we know are contained in our function. So let's go ahead and use those, and all we have to do is connect the dots, and we have our function. So our first one is minus 2 and 0. We have minus 1 and 1. Oh, right there. We have 0 and 2. 0 and 2. We have 1 and 3. And we have 2 and 4. Okay, so this should make as close to a straight line as possible, and it should contain all these points. Okay, now our domain here is actually the set of all real numbers, as is our range. So this line is going to, in fact, extend infinitely in both directions, and we're going to assume that it's continuous, so it contains all the numbers in between, and that's actually what the definition of all real numbers is. So this is our line for f of x equals x plus 2. So let's go ahead and do one more. Let's say we have the function f of x equals, let's say it equals 1 minus 0.5 to the power of x. Okay, we haven't seen one of these before, so let's go ahead and see how we deal with it. We're gonna approach it the same way. We're gonna make a table of values, and our domain is going to be x. Our range is going to be f of x, or our function evaluated at the given value of x. So let's pick out a few numbers. There's actually nothing. Our variable is actually our exponent, which is kind of different. So there's actually no numbers that we need to stay away from, but rational numbers, we kind of don't want to. We want to choose some integers, but we want to choose some negative and positive integers. So we can go about actually the integers we've been using. Minus 2, minus 1, 0, 1, and 2. The reason these are so useful is because we're getting a taste of both the positive and the negative side. And plus they're kind of small, so they're easier to work with as far as calculations go. Okay, so we want to find f of minus 2. So when we plug in minus 2 for our exponent up here, what does this function equal? So we have 1 minus 0.5, so we have pretty much 1/2 to the minus 2 power. And that's going to give us, well, if we want to write this out, we have f minus 2. Let's go ahead and show you what we're doing here. So we have 1/2 to the power of x, or actually the power of minus 2. We'll see in a later video when we're working with powers of exponents that when we have a negative exponent, we're going to drop the fraction, or whatever this term is, into the denominator and put 1 on the top and make the exponent positive. So essentially what we have is 1 over 1/2 squared, which gives us 1 divided by 1/4. 1/2 times 1/2 is 1/4, which gives us 1 times 4 over 1, If we flip the second and multiply, we know how to deal with rational numbers, which gives us 4. Okay, so f of minus 2 equals 4. Now we want to know what f of minus 1 is, and we deal with that pretty much the same way, and we result with f of minus 1 is 2. Now f of 0, anytime we have 0 as an exponent, no matter what is in front of it, we always get 1. That's just by a rule. It doesn't matter what is in these parentheses or what's in front of the exponent. If we have an exponent of 0, it's always equal to 1. So it kind of makes life fairly simple when you have an exponent of 0. Alright, so we want to know what f of 1 is. Well, f of 1 is just 1/2 to the 1 power, or the power of 1, which is just 1/2. Now we're going to have 1/2 squared. We saw down here that 1/2 squared is 1/4. And let's go ahead and use one more value, x equals 3. So we're going to have 1/2 cubed, which is 1/8. So now we have a nice set of values here. So we have plenty of points. Let's go ahead and see what the graph looks like. It doesn't have to be very pretty. We just want to get an idea of what we're working with here. So we have our f of x-axis. We have our x-axis. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. And let's go ahead and put a few down here. All right, so let's go ahead and plot a few of these points. So we have minus 2 and 4. That's a point right there. Minus 1 and 2. Right there. We have 0 and 1. We have 1 and 1/2. We have 2 and 1/4. And we have 3 and 1/8. Now we saw something like this, kind of similar to this in the previous section, where our function is going to approach at least one axis, in this case the x-axis, but it's actually never going to get there because it's actually never going to get to f of x equals 0. F of x can never equal 0 here because no matter what, since our variable is the exponent, we can plug anything in here that we want to, and our function will never equal 0. No matter how large of a negative number we put in here, or no matter how big the positive number is that we put in here, heck, we can even put in 0. We put in 0 here, and it's just simply equals 1. So our function will never reach 0 here. So it'll infinitely and indefinitely approach this axis, but it'll actually never touch it. So it's kind of theoretical, which is very cool to think about, and it'll actually approach infinity in the other direction, and it'll go on forever and forever, since the domain is a set of all real numbers. It'll go on forever. So very cool to think about, and so we're dealing with graphing functions here. So one last time, we're taking our function and we're creating a table of values here that actually makes graphing the function much simpler. Because we're picking values to plug in for x. We want to be smart about them, so we're not getting anything over our head or anything too difficult for us. And we want to pick some easy points to where I can plug into our function and actually get the range, so we can plot some points, connect the dots, and see what we're working with. This is very important. We'll actually be dealing with it a lot more in the future sections. So I'll see you soon.